Hello, good evening. This is demo for Milestone 4, ELE 604. Before we get started with the demo, I'll just run the code so we can see it properly. And we'll see the first thing coming up are the names with the milestone. We can scroll through every milestone by just pressing the switch. And we'll have about 4 different states. One of them will be sending MATLAB code. The first state that we will cover, before the first state, there's actually a safe or unsafe display sheet that can be enabled if you double click right before the welcome screen, and it will show you the condition of the LEDs and of the microcontroller, the accelerometer, and the weight, whether the mass is in danger zone. When we cover the state 1, and that will cover basically acceleration, as we can see it's fairly accurate in the reading. We have about 90 degrees here, and that's 90 degrees in the middle, 91, 94, and that keeps a track of it. We'll move it all the way up to this. So that's actually about 150, and as you can see there, and you'd have the same reading in the microcontroller itself. So as covered in the previous milestone, the accelerometer works with tangent formula and basically the interrupt vectors, which will be placed on these 2 pins at the top. One thing that needs to be said about that component and the LEDs is that after wasting about 2 days now, and it's been 72 hours, this is the last night I will spend on it, I had to conclude that even though I looked up all registers in detail, the ports, digital ports, are quite limited. So it wasn't possible without removing my circuit to another configuration to actually get the LEDs working with the accelerometer at the same time. All the ports that I've looked into are either taken or grounded by like internal measures, and basically what I ended up doing is draw out the whole layout and try to figure out which ports would be available for configuration. That didn't work, and I was 1 port missing, so that just explains that the LEDs should not have been configured on the top 3 pins on the PT 1, 2, and 6 here. So that could have been the issue for that. Moving on to the next state, and we covered that the LEDs, the 2 LEDs don't work because apparently those 2 pins get overlapped, right? So that's that. Next state, we will cover that's state 1. State 2 is weights, and it goes with the weight cell. It's fairly accurate, so now it's reading 2930 grams, and that's a 29 gram output. The circuit is really sturdy, and it's made up with all the alligator clips that can be attached to the pins outside. It's very sturdy, and it's basically plug and play because everything goes in series, so there's no thinking when it comes to connecting the whole board, and it could be set up in minutes. And the same thing goes for the board itself. The only component left over that I never ended up implementing is the accelerometer itself, because it did cause issues with the LEDs, and by this point, spending about 2 days on trying to figure out a software solution, I do have to say that that was not worth it, and I should have just removed the pins to another location. Would have solved a lot of issues. There were some really weird issues happening when I did try to connect to the following pins. So I tried the PT4 pin, and you can see it really from this, and the PT3. It did cause some issues, especially when I connected to PT0, because everything would just stop working after a few minutes for no reason whatsoever. And yeah, so that's basically the project. That's the weight standard. I have to show all the weights just for proof. So I'll remove this, and let's say it's 0 grams. So we remove this at 0 grams. So So we got no weights and 0 grams, and we have the exact same reading. Now I did make an adjustment because from 0 to 2 grams it can't really tell, so below 2 grams I just said approximate to 0. So that's one thing. Let's try the 61 gram. Hold it. So we tried the 61 gram, and the 61 gram would get this reading. We move it a little bit over to the side. So if we see right now, it's about 59 and fluctuating, right? So that's fairly accurate, right? Yeah, so these are basically the readings. Now, what happened with the calibration for the load cell? I did something interesting that I basically read out all the values from one of the load cells here in the lab, and I created this map of values that approximated with that system. So the load cell I used had these value readings after I did the tweaking of the board here with variable resistances, and having this basic table is a nice, small and quick way to just do calibrations for basically all load cells, and I was able to do this in a few minutes. The whole idea of it is to measure with the digital DMM these two pins, or maybe the output pin. Either way it works. So for this table I have the Vout values of the output pin. So you'd basically measure the output voltage DC, and you'd match it with the weights values that you'd see, and after doing that tweaking and measuring, and everything could be done by just tweaking the resistor connected to one of the one of the positive or negative sides of that. So by editing that, you'll be able to get these values in this format. And out of this table, I was able to compile a and this is the previous labs, of course. I was able to compile a MATLAB matching, and the linear model was best fit for the MATLAB match. And by using that model and a specific formula that I created for outside of that model, I'm able to calibrate basically any load cell in a few minutes. So this is a compact way, I would say, of how to put this component together, right? And before we can move on to the next state, and that's basically the next state will contain less information, so it won't contain force, and it'll just contain both values, and it's right here. It's this one. So it will contain both values of angle and mass, and we can move this to about it's a bit out of focus. Anyhow, moving the reading for the angle. So if you see here, it's about 40, and what is it? 45. No, this is 50 here in the middle, and you get 55 and counting. So yeah, that's basically all those components. Apologize if the video is a bit blurry and I'm moving too much. That's never done this before. So the last portion, however, is to send data to the MATLAB, and that was not fairly possible to read with these machines. We can see the light showing up there, and that's the RX pin. So that's the TX pin. So it's transmitting, and the light, everything lighting up, showing that the data is sending correctly. It's a problem reading it through these computers, because one main issue that I saw is that the virtual machine takes control of the COM port and doesn't let the MATLAB, which is located on the other machine on Linux, to read off that COM port. So displaying that is an issue on these machines. I still don't have my laptop, so I couldn't really get it running there, and it'd be a lot easier to show. However, I'm confident that all these components work fine. The whole lab works fine. I've studied this in great detail, as you might know. I am very sad though, because I did buy other special components. I got a little AC. I got a little active buzzer, so it works on the analog pins, and could have been tweaked to make noise every time the LCD goes in warning sign, which I didn't show because we can have it right here. On the second state, let's say we apply incredible amounts of weight, so I'll just like hold on to it like this, and you could see that by exerting too much force there will be an error max reading limit, right? So that's a good way to tell of what's happening in reality. And the maximum reading is about 220 grams, and that's the force equivalent to it. This is basically all the lab, covering all components. Yeah, and the casing at the end, fairly sturdy, nice and simple. Everything is locked in. It looks good, and that's that. The other part, we just have to remove the top. Was not configured, but the rest is fine. I even made a little cut through the board. And basically what you do is right here, like that. Right, and that's that. And we could see the screen here, even though it's blurry from the phone. Yeah, so that's basically it. Thanks for your time, and have a good night. Sorry for the delays, for everything. It proved to be a good project overall. We did get to learn quite a bit, and yeah, thanks. I'll send out the report and everything soon, right about, yeah.